Here we will have another example to be able to see the scaling effect on pivoting. So we have three cases. The first one, we simply solve these equations using Gauss elimination and pivoting. And in the B, we will simply scale the equation so that the maximum coefficient is 1, then solve the equation. Here, for instance, this is very large. We need to have this to be 1. Finally, use the scaled coefficients to determine whether pivoting is necessary. However, actually solve the equation with the original coefficient values. So for all cases, we will retain 3 significant figures. The correct answers are these. But for 3 significant figures, of course, this is just 1.00. And x2 is, again, not 0.99, but we have to round it to 1.00. So let's check the results. So in part A, we will have Gauss elimination and pivoting, but without scaling, basically. And that's why what we need to do is simply, we will have pivoting. But for the pivoting, we already have, so for the first unknowns columns, we will have the largest coefficient here already. So this is already pivoted. That's why we simply use this and multiply the first equation by 1 divided by 2. 1 is the coefficient of this. Then from here we will have x1 plus 50,000. x2 is equivalent to 50,000. The result is this. And we subtract this from the second equation. Second. If we subtract, x1s will be eliminated. And x2 is actually minus 50,000. Actually, it's minus. So let's say this way. So here we have 1, and here 50,000 is subtracted. So this is minus 50,000, which becomes minus 49.999. But we will need to have 3 significant digits. Again, that's why it will be 50,000, but minus. So minus 50,000 x2, and same as the this result, 2 minus 50,000, which becomes again 49.998 minus 49.998, but for 3 significant figures, if we consider, it's again minus 50,000. So we use this as the second equation, and the first equation is this. Here actually we can simply find x2 as 1.00, and if we put this into here, then x1 is, from the first equation, x1 is 0.00. I mean, you can write here for 49,999 and minus 49,998 as well. If you divide, we will get again 100 actually. Not a big change. Just the book solved with 50,000, that's why I solved with those as well. But x1 will be 000 in 3 significant digits. So this gives us, if we compare with x1 is 100, like very wrong, 100% error for this one. So in the second part B, actually, we repeat the solution after scaling the equations. So we simply scale these. What it means is that we want to have the largest coefficient in one equation to be 1. So here this is the largest. So we want to have this to be 1. So we simply divide each coefficient by 100,000. If we divide it, the first equation will be, let me write down here, part B, the first equation, so divide by 100,000, which gives us 0.00002x1 plus 1x2 is equivalent to 1. In the second equation, the largest coefficients are already 1, so we keep that x1 equals 1. So the rows now should be pivoted. If we apply pivoting here, we need to move. You can see that for the first unknowns, the largest is here. We will have this as the first equation. Then switch these, pivoting. Then 1x1 plus 1x1 equals 1. 0.0002x1 plus 1x2 is equals 1. So we applied this. Actually, this is wrong, I think. Yes, these are 2. 2 and 2. Because here it's 2. If we solve this by partial elimination, simply we will multiply the first equation by 0.0002 divided by 1. And subtract this from the second one. You can do the operations by forward elimination. We will just simply find x2 as 1, 0, 0. Then x1, if we put this into here, this is x2. This is x2 too. If we put this here, then x1 is simply again 1.00. So we obtained the same correct answers. You can see here. These are the same. So scaling is important. You can see in the first one, if we summarize, in the first one, we applied pivoting, but we didn't scale this. And we have a problem of having a large error. But we used scaling and had the largest coefficient 1, then applied pivoting, then we were able to find the true results. So this is important. We will both apply scaling and pivoting before Gauss, while doing the Gauss elimination. Let's go to the part C. Use the scaled coefficients to determine whether pivoting is necessary. Actually, we will solve the equation with the original coefficient values. So we will solve these. So what we need to do is simply we will make a scaling. So we will have these to see if pivoting is necessary. So we see that pivoting is necessary. We will change the order like this, but we will use here the original coefficients rather than using these. So we will have the pivoting after scaling, but we are not going to use the scaling while solving. So that seems to be confusing, but simply so with scaling, so we have these equations. Pivoting is necessary. We see this. Then we will pivot it, but with the original pivoting in scaled, but use original coefficients to solve. So we simply change the order here with the original coefficients. Simply, we will have 1x1 plus 1x2 is equivalent to, and as the second one, we have 2x1 plus 100,000 x2 equals 100,000. Now here we will multiply the first equation by 2 divided by 1 and subtract this from the second equation. Then from here we will solve x2 again. Here we will find x2 is 1. And if we put it here, we will find x1 is 1, 2. So the scaling was useful to determine whether pivoting was necessary. But the equations themselves did not require scaling to arrive at a correct result. So what we mean is that scaling is important, but we don't have to use the scaled coefficients to solve the Gauss elimination. We can again use the original ones after we do the pivoting based on the scaled coefficients, let's say. So C and B are good enough to solve, but A is not good because in A we didn't use scaling. So always try to use scaling to get correct results. That's the important point here. You can use either the original coefficients once you did scaling and pivoted the elements, then you can use the original equations, or you can use the scaled equations. I mean, the both will be okay. In this slide, we will be further talking about scaling or normalization. And as we did in the previous slide, in the example, the normalization will be important to be able to have a correct solution. And first of all, if some of the equations in a system have much larger coefficients, like here or in the previous example, than the others, scaling should be applied to minimize round of errors so that we can find the correct solution. However, scaling itself also leads to round of errors. For example, here we have these equations, and in here, if we want to have a normalization of this, actually we have only this equation. If we want to have a normalization, we divide these values by 300,000 and obtain this equation, as you can see here. And with three significant figures, you can see we have these values, but of course there will be further values here and here. Because we only used three significant figures, we actually lost some magnitudes of the values. So this will lead to some round of errors. That's why the scaling introduces a round of error to the coefficients and constants. The coefficients are here and the constants here. For this reason, scaling should be employed only as in part C of example 910. So in the previous example, in one slide before, we actually used in part C the scaling just for pivoting, but after pivoting we use the original constants and coefficients in the original equations. So for pivoting you can use scaling. First scale the equations, then perform pivoting. After that use the original constant and coefficients. So that's the part C in example 910. If you don't remember, you can go back to a previous example and understand what part C is. And it is used to calculate scale values for the coefficients solely as a criterion for pivoting. So this is important. Use scaling or normalization just for pivoting. Then after pivoting, don't use normalization, but use the original coefficients. So the original coefficients are retained for the actual elimination and substitution operations. But this involves a trade-off if the determinant is being calculated as part of the program. So because the reason is that we said that the determinant will be calculated using the diagonal terms of a matrix after the elimination process. So we will have an upper triangle after the forward elimination. Then we will use the diagonal elements, multiplication of them, to calculate determinant. And for the determinant, using normalization is better to be able to have a better evaluation of the determinant, because if the determinant is near zero after normalization, then we have an ill-conditioned or singularity problem in the systems of equations. But we said here that we will not use the normalization while doing the elimination process. So then for determinant we need to use normalization and then elimination. But in finding the solution, we will not use normalization, but we'll use elimination. So this brings us a trade-off. And that's why if we use this part C methodology, meaning that use normalization for pivoting, then use original coefficient values for elimination, then the resulting determinant will not be scaled, will be unscaled. But in many applications of Gauss elimination, we don't need to calculate determinant. That's why we can still use this and no need to calculate determinant. I mean, after elimination and substitution, if we can plug the the calculated results into the equations and check the results. If these are correct, then we can say that okay, we have a good systems of equations rather than checking the determinant in that scenario. But if you really want to find the determinant, then you will do normalization and then elimination as an additional step maybe. So the most common approach is just use the scaling or normalization for pivoting, then use original coefficients for elimination and substitution. So we will show the algorithm for this process in the next section, in the next slide actually, and let's check that in the next slide. Meaning that we will use scaling or normalization for pivoting only. Scale values of elements are used to determine whether pivoting is to be implemented. After that, we will use the original terms. And the diagonal term will be monitored during the pivoting phase to detect near zero occurrences to flag singular systems. So rather than calculating the determinant, we will just check the diagonal terms. If these are near zero after pivoting or during pivoting, then we will say that there is a singularity in the system. And the pivoting is actually here the algorithm. Basically, we perform the division to have a normalization, then have actually here a dummy variable to be able to get the pivoting, obtain the pivoting, as you can see. So on the left hand side you see the Gauss function, and it actually has three for loops we said earlier in the naive Gauss elimination. We use the same here. The first two is here again, but the third one is in the eliminate function. So this eliminate function will be the Gauss elimination actually, and in here we have the third for loop. You can see here we perform the division and subtract from the equation below it. Also the constant values, we subtract them as well and obtain the result. And we have a tolerance here. If the tolerance is smaller than this, the division of this, then there will be an error which gives us a singular matrix, meaning that there is a singular system and it's a problem. So division here, if it is smaller than a tolerance value, which is very close to zero, meaning that we have a division by near zero, and that's a problem. Or in the pivoting we will have a near zero occurrence. If it passes back a value of r equals -1, a singular matrix has been detected and computation should be terminated. So that criterion is here. And the tolerance is set by user to a small number to detect near zero occurrences, as we said here actually. And here as well, we should check here too. So pivoting is here, and also substitution function is the same as in the naive Gauss elimination. So this will be the same as we mentioned previously. So this is the basic idea. You can use these four functions to write your own MATLAB code to be able to get the full Gauss elimination, including pivoting with scaling here. But after pivoting, we will not use scaling. We will use the original coefficients in here.